Hello, and welcome back to Learn It from a Layman. I am Carl Christensen, back again with Cameron and Matt. Tim will be joining us later. He is slowly finding his way out of the artificial intelligence that consumed him. So he should have some tales from the other side. And today we're joined by Curtis Rands. So welcome to the podcast, Curtis.
Thanks for having me.
Yeah, thanks for coming on. So a little bit about your background. You can say anything I miss, but Curtis, you're a mechanical engineer. You've worked in the field for 15 years or so, and you have a master's degree. So you've got your credentials up on mechanical engineering, right?
Yeah, I suppose so. Yep.
Okay, and today we're going to be talking about some of the basics of mechanical engineering. So we appreciate Curtis coming on to fill us in. So Curtis is our expert. Matt's going to fill in what he might have some familiarity with as well. And Cameron and I are going to nod our heads and smile. Um, but let's go ahead. So I guess the first question, Curtis, is what kinds of problems do you solve as a mechanical engineer?
Okay, yeah. So I guess just very broadly, engineering is kind of applying scientific knowledge or scientific principles to solve problems, and they're problems with like our everyday life, right? So mechanical engineers specifically solve problems that have to do with things that move or have moving parts. Um, and we often deal with systems and kind of their relationship with energy. And so, like, for example, systems that generate energy or really convert energy from one form to another, systems that take energy inputs and do useful work or produce a useful output with those. And then there's also systems or things or products that have to deal with maybe like some energy that could have like a potentially negative impact. So some examples might be like sporting equipment, uh, like a golf club. It doesn't have any moving parts, but it moves, comes in contact with the ball. So, you're kind of using the energy to do something useful, right? Or, whether it's a tennis racket or a pair of skis or something like that. Um, Other kinds of, so kind of another example would be like a wind turbine or a giant stationary gas turbine that generates energy. So it takes like, you know, wind energy, converts it into some useful output, or takes, chemical energy from burning fuel, produces some useful output. And then kind of the last thing, things that deal with energy that might cause like a negative impact would be like a spacecraft. And I know that maybe not very many people have direct like experience with the spacecraft, but most people have seen a
Not
spacecraft
yet.
launch, right?
Yeah.
And yeah, that's right. And even though that's often far away and it's kind of not as upfront and real when you're not there, but um, there's a lot of force generated to get out of our atmosphere and out of our kind of gravitational influence or far enough out of it, and you put this very important, very expensive, probably fragile scientific instrument or some other kind of device on the end of a rocket and launch it, and it's subject to a huge amount of vibration and a huge amount of thermal energy as it's leaving, going through the atmosphere, again when it re-enters, if it's a re-entry vehicle, and then also when it's in orbit. It's like all day, all night, 90-minute orbits or whatever. It's in the full, getting the full brunt of solar energy, and then it's in the full dark and like cold of space in these cycles. So those are kind of like some examples, but the problems we're solving is like, how do we make the products and the infrastructure that we have every day safer or better, and perform better. And often we have to say, what's a material replacement we could do? What's the current physical limitation of this product? How do we use our scientific knowledge of physics or material science or something to push it past its current limitations, to make it do something that it currently doesn't do today.
Okay, so you gave us a bunch of examples of like what some of these different roles, I guess, different ways that engineering concepts could be applied. But what are like, is there like a standard way to apply engineering, if either physics or whatever it is, to an unknown project? Like if you get a new project in, are there basic engineering considerations that you can apply to it across the board, or is each project different enough that there's no one way to approach the engineering assignment that you have?
Yeah, so there's definitely like an engineering approach, right? I mean, it's really like the scientific method, which we've all learned, and there's kind of a bunch of different ways you could put it in order of different things, right? But there's an engineering method, and it's kind of like define the problem, define what the requirements are for a potential solution. Then think of all the physical things that, kind of rules or ways that you could address the problem. So kind of like this brainstorming, concept generation kind of stage. And then you have to figure out reasons why certain concepts wouldn't work and kind of get down to a few concepts that could. And then you kind of flesh those out a little bit. So now you go from like a conceptual design to a preliminary design. And then you're getting further down trying to figure out, each time you make a little bit more detailed kind of step towards what you think your solution will be, you also better understand the potential like obstacles between where you are and your solution. And so now you have to address those. And it might be do a test, do a computer simulation, do a hand calculation, create a spreadsheet with some calculations, build some prototypes and figure out like which parts of the structure you kind of don't fully understand, improve your design. And you get into this part where you're kind of like doing like a cyclical, like design, test, assess, go back to designing, and then at the kind of the end, you now are ready to document a design in preparation for producing it, manufacturing it, whether it's in small quantities or high volumes, and then you you produce your product. And at the end of that cycle, you now have this documented idea, and you've produced it. And now you go into something like maybe like you call it like sustainment engineering, where you're doing new versions, improved versions of the product, or dealing with like the marketplace. Oh, this thing is breaking when we didn't think it would. Let's figure out how to modify it, improve it, and make it better. So that's kind of like the general approach. Now, there's tons of disciplines even within mechanical engineering. So some problems are problems to deal with like a thermal environment or thermal loading, and some problems are purely structural, and some problems are a mix, and some problems are controls problems, how to make something behave a certain way and minimize the error between what it's doing and what you want it to do. And there's also, of course, like multidisciplinary problems where you have electrical engineers and mechanical engineers working together, or civil engineers and mechanical engineers working together. So, but within the discipline of just mechanical engineering, there's all these different disciplines depending on the problem you're trying to solve. But pull in a few of those different disciplines, and you'll focus on a relatively small number of equations or physical principles that are the things that are making it challenging, especially with how far we've advanced in society. A lot of times you're not doing something brand new. You're just kind of riffing or improving or innovating on something. So you've already solved a bunch of the problems, right? And now you're like, well, what if we could, electric cars are a great example, because a lot of the stuff of a car gets transferred over. I mean, I know you're not just removing an engine and putting in a battery and electric motors, but they got four wheels, they got tires, like all the engineering of tires, right? And all the engineering of making the cabin quiet and comfortable, the road noise and brakes and bumpers and things like that. You can bring those over. You don't have to start completely from scratch.
Okay. Yeah, that all makes sense. And like you said, it's a huge field. One of the layman problems that I get into, which is why this is called Learn It from a Layman, is that, trying to understand the field of mechanical engineering in about a 1-hour podcast turns out not exactly doable. Unless is that how long it took you to get your degree?
Yeah, but we don't admit to that.
That's right. This is the beginning and the end. By the end of the podcast, we will write people our own certificate of engineering qualification.
Well, we could just send them like some overalls and a hat and say, "Now you're an engineer. Go drive a thing," right? Confuse it
Right.
even more.
Yeah. I was thinking, kind of Bob the Builder type feel. Throw that out to people. Congratulations, you can now go work with Manny and build a house.
And that's where we'll get exactly. I'm sure that at the end of this, anyone that wants a job can apply with Curtis, and then they'll be or not. But let's get into a few of the actual principles, I guess. So these are, once again, Curtis, we've gone through these pre-shows and some of the questions, but this is coming from a layman, so some of these might be out of order or entirely nonsensical. So just add whatever. Okay, so tolerance. It's a word I'm familiar with in engineering. What is tolerance in engineering as opposed to tolerance as in tolerating Tim, for example? And how do you measure tolerance?
Yeah. Okay. So, I mentioned that once you've got a design that you're ready to produce, an engineer will document it in the form of engineering drawings or manufacturing drawings. And so the drawings, in the case of a fairly simple mechanical structure or static structure, you'd have a drawing that would have a picture from different angles of your parts, and you would dimension things like the length of the part from one end to the other and the height of the part. And if you imagine, I actually have, obviously this is not audio only video, but I've got a ruler. If you imagine like a structure like this that had a bunch of holes in it, and you had another person designing the other thing that bolts to. If I just told him exactly where the holes needed to be, and I told him what size bolts we were going to use to join our parts together, and we just made the holes the exact same size as the bolt, and I didn't tell them, I didn't give him any wiggle room, because that's effectively what tolerance is. It'd actually be impossible for anybody to make a part that meets that drawing because we didn't give them any leeway, and you can't actually drill a hole of perfect size. The bolts don't come in with perfect size, and you can't put a hole in the exact right spot. Machines don't do that. People don't do that. So we might think they're very precision, but that actually, there's error in everything we do. So instead, I would give that hole a little bit of clearance over the bolt. And I would also tell the other person designing the other interfacing part, what I think the tolerances should be, what I think for the positions. And I would communicate that on my drawing. They would communicate it on their drawing. And we would do it in such a way that we would guarantee that when our parts come together, the holes line up enough and the whole size has enough wiggle room that you could put like 3 or 10 or 100 bolts through, and every single one of them would fit through. So if you make the holes too large, maybe the bolt falls right through because it's larger than the head of the bolt. Or maybe you can't line your parts up, you put it together, but whatever it's supposed to do, it doesn't do very well because it's too sloppy. But if you make them too tight, you might not be able to put more than one of those bolts through. None of the other bolts will fit because all the holes are off by a little bit in the wrong direction on the two mating parts. Once you get past the first two holes or the first couple holes, or there might be just like one that's way off. So tolerance is a way that we define this hole needs to be a 1/2 inch plus or minus 20 thousandths of an inch, and the whole position has to be at this location, but it could actually be in a circle that's, anywhere within a circle that's slightly larger than, or that's like 20 thousandths of diameter, relative to like the center line of that hole. And the drawing effectively becomes a contract between you and the person who agrees to make the part for you. So when you give them that drawing and they give you a price and a schedule that they're going to produce that part for you, they're also agreeing to your tolerances and that they're going to make it to your tolerances. And when they're done, you'd probably ask them to produce like an inspection report that shows they measured all the holes, maybe spot checked a certain number of the holes or a certain number of all the parts they're making for you. And they produce a report and said, we're within spec on every one of these holes, on the position and the size, on the length and the height of your structure, on certain features. And that guarantees that those features will mate up with their mating part, their interfacing part. So that tolerance is what I can tolerate, what the part can tolerate to do its job, and to actually go together with all the other stuff that it's supposed to interface with.
Okay, that makes sense. And it's essentially the real world application of mathematical engineering principles is tolerance is that's my understanding. It essentially is we know that it's imperfect, that these various processes are imperfect, so we add the tolerance to say this will function and this design will is able to handle these differences.
Yeah. And for like a pattern of holes, two parts that bolt together with a bunch of bolts, for a pattern of holes, if those are there's actually a pretty simple way to calculate, like if you want the holes to be a certain size, then what position you need to put for all those holes to give you not just like a good chance, but 100% chance that as long as the parts are made, that those will mate together. But there's other things where the tolerances are not obvious, and what you can tolerate is not obvious. And so you might have to do like a calculation. Maybe if I'm designing some super high-speed vehicle and it's riding on a track, I have to understand what effects being at the very bottom or top end of that tolerance band will have on performance or safety or noise or vibration or whatever. So I might have to do a test and say, okay, let's assess this at the very top end of the tolerance band or the very bottom end of the tolerance band and do a test for this particular feature. You don't have to necessarily test the whole vehicle. And you also, if you have lots of things attaching together, you have tolerance stack ups. So you have to consider if each thing happens to be made at the very worst end of its tolerances, will all the things fit together? What if one's made at the top end and the other one's made at the bottom end of its tolerance? Will it fit together? So there's some calculations and some processes you do, but a lot of times, a few features you have to really focus on. The other ones you can just use like these guidances, rules of thumb that have already been established. And it's actually not, tolerance engineering is kind of just a thing you have to do, but it's not something you focus on too much unless you're doing something new that's never been done before and you don't understand how much precision is required. But precision costs money. So I can't just say, well, just make it really small and really tight tolerances. The machine shops will charge you for that. They'll say, nope, there's no way I'm going to be able to make those tolerances on the first part. So I'm going to charge you for 10 parts because I'm sure my 10th part will be good enough. But I'm only going to get the 10th part. I'm not going to get all 10. They're going to charge me for 10.
Right. Interesting. That's really insightful. Okay. So I think we'll come back to this idea a little bit later in the podcast with one or two of my other questions as far as when things might explode or people might die. But what are static and dynamic forces?
Yeah. Okay. So dynamic really just means something's changing with time. So, and static means it's not really. Now, engineers are good at approximating things. I don't know if you've ever taken like a physics class and they say, okay, just assume there's no friction or whatever. Engineers don't say, well, we can't assume there's no friction, but we're going to approximate it. So sometimes things that are moving and changing with time we might be able to make a case that we can still treat them like static systems because the way they're changing with time is not going to be impacted by the way that system responds with changes in time. So let me unpack that a little bit. If I'm just doing like statics of a structure, what I'm assuming is that the structure is, or a system, any kind of system, I'm assuming that the system is not accelerating or decelerating. So it might be moving, which means its position might be changing with time, but it's not accelerating or decelerating. So I can use Newton's law, Newton's first law, which basically says the sum of the forces is zero, because I don't know, Newton's first law is like the sum of the forces equals mass times acceleration. Well, if there's no acceleration, then I could say the sum of the forces is zero. And I could say, some like a ladder leaning up against a wall. It's very basic statics calculation. And you say, I want to know like what angle before the ladder slips, or I want to know what if you put the ladder on like a really slippery floor, what friction coefficient would you have to figure out before the ladder slips? Well, the ladder slipping sounds like it's moving, right?
This is information I could have used like a few years ago, but yeah. Well, let's continue.
but I'm only interested in like, when does it start to slip? So as long as I can show that with a certain friction coefficient or at a certain angle, it doesn't slip, but at any steeper angle, shallower angle, I guess, or at any lower friction coefficient, it will slip. That's a statics problem, right? So I can box it in, like what's safe,
okay,
and anything outside of that acceleration will actually start to happen. So that's static system. Dynamic system has acceleration. So it might be like a car going around a curve, and now it's actually accelerating or decelerating, or a car hitting a tree, decelerating, right? So that's statics and dynamics. You can also have a structure that behaves dynamically. So if the structure vibrates at a certain frequency, maybe like you have a bridge that's in a windstorm, it's a rope bridge or something, a cable bridge, and in a windstorm, it vibrates at a certain frequency. You could say, I'm going to assume the bridge is static as long as the wind forcing that bridge to vibrate at a frequency that's quite a bit lower than its natural frequency. Everything vibrates at a natural frequency, so I don't want to get too far into that, but if the bridge vibrates at 100 hertz, and a light wind would potentially cause that bridge to vibrate at 5 times per second. 100 hertz is 100 cycles a second, and maybe that bridge vibrates at only like 5 times per second in the wind. It's never going to hit like that dynamic behavior. So I can just say, I get that it's moving, but it's not moving enough to like start for the dynamics of that structure to have a negative impact. So I treat it like a static system. So then there's other things, like you could have like dynamic events like heating and cooling cycles. You could have other things that are dynamic, but it's really, dynamics means changing with time, and whether it's a dynamic system or a dynamic structure, or it's fluid dynamics versus like fluid statics is a thing. It's the fluids are moving or changing with time versus like fluids in a pressure vessel, and you're just dealing with like pressure at like a kind of static state.
So would you deal with something, like an earthquake would be like a dynamic force? And is that something that you would engineer into either a bridge or a building?
Yeah, absolutely. We have our company does engineering services, and so people come to us and say, "Can you help us solve this problem or whatever?" And we have an artist make sculptures, like big, huge, really cool, like metallic sculptures. And sometimes they're not that big. Sometimes they hang on a wall inside somebody's house. Sometimes they sit on somebody's poolside or something. But sometimes they're big, and they go outside in front of like some fancy biotech building or something like that. They're huge. They have to pour concrete and calculate the decide what the foundation is going to look like, and they'll come to us and give us some information, give us a model and structure, and we will calculate wind forces on it and hurricane loads on it, and give an output of like how strong the foundation needs to be able to handle the things you'd expect in the location it's going to be located, so it doesn't fall on somebody.
Okay, so sorry to keep diving into this one, and I'm not like I expect you to have an answer to this, but like 2 or 3 years ago, a building like collapsed in Florida, right?
Yeah.
Like completely, just suddenly went complete pancaked, right?
Right. Yeah.
Is that an engineering issue? Is that just a lack of maintenance, and their initial engineering was fine, but you just have to keep these things updated, or what is your insight on that?
I can't remember all the details of that, so I'm not a civil engineer and I don't work with buildings, but because I do work with structures and I do sometimes do engineering calculations, I listen and I pay attention when some of those things happen. But that one was a little bit long time ago. But my understanding was it was a maintenance issue. But it was a known maintenance issue, if I remember right, that like they basically neglected to maintain it. And even though some people spoke up and said you should do something about it, engineers said you should do something about this. I think the building owner didn't or something. I don't know.
Okay.
But
all right.
Yes, so a building could be built before the engineering codes, or a bridge or any structure could be built and designed before the engineering codes were upgraded for like better understanding of how earthquakes and dynamic events happen, because buildings are built to codes, and the codes are designed to be like, if you work within the code, you don't have to even really do hardly any special calculations. You just follow the code. But if you don't maintain it, or if the code gets upgraded, kind of are subject or at risk that
Okay.
an event could cause damage. Yeah.
Got it. Okay. Thanks. Okay. So next question, in my layman research into this, there seem to be different types of pressure. Maybe that's a layman misunderstanding, but what are the different types of pressure, and how does that go into engineering considerations?
Yeah. So pressure is really just force applied over an area. Okay. So if I have a pressure vessel, which could be like a gas tank or a fuel tank of some kind that's pressurized, and it might be rocket fuel, it might be a spaceborne structure. I have to be able to handle, like, you're trying to pack gas or some kind of fluid in there. Usually it's gas because you can pressurize it, right? But you're trying to put as much as you can in there. And as you keep jamming more in there, it increases the pressure. And then gas wants to escape because the gas on the inside is, would much rather expand compared to like the outside environment, especially when you're going into space. There is no pressure outside. So no matter what pressure you charge the tank up to before you launch your spacecraft, once you get into space, it will be under more pressure than when it left, when it left Earth. So you have this gas that's trying to escape, and everyone's blown up a balloon and had it pop on it. And that's what's happening, is you're putting more air in there than would normally want to fit in there if it was at temperature and pressure. And it wants to expand and blow up. So the pressure that balloon sees is actually a force of something trying to applied over an area. So another kind of pressure could be like people walking on a structure, and they all have their certain weight or whatever, right? But your foot doesn't have an infinitesimally small area. It's got a surface area. So every time you take a step, you're applying a force over a certain area. And if somebody's walking on a roof, with, or a bridge or something, some kind of structure, wearing high heels, they're applying much higher pressure there for the same weight than if they're wearing, tennis shoes or something, because all that force is concentrated to a smaller area. So any kind of time when we talk about pressure in engineering, at least, we're simply talking about like a force applied over an area. And whether it's a fluid pressure, it could be a gas, could be a liquid, or it could be two structures in contact and one's applying a force on the other, and that's how it's applied. Now, if you had like a beam, and again, like the bridge, you could think of a bridge, and you're putting a force on a beam. Well, that beam's trying to support that force. So at its attachment points, it's kind of trying to like bend, and all that force is being being transferred through like a bending load to its attachment point, and now the area or the size of that beam will depend on how much pressure is actually being applied to like all the structure of that beam, not at the place where the load's applied, but at the place where it's attached to like a wall or something. And we actually call that stress. When we start talking about like mechanical structures bending or breaking, we call it stress. But stress is the same as pressure. It's just force over an area, like distributed over an area.
Okay. That makes sense. And different materials obviously then handle pressure differently, right? So I mean, like you said, a balloon under pressure pops, but a concrete structure under pressure just will crack essentially, and that just is that I mean, obviously that's one of the things that you the different materials handle. I can take different loads of pressure as well, right?
Yeah, absolutely. So I know, sometimes people will read articles about things like I don't know, like spider silk. They'll say, "Oh, spider silk is stronger than steel," and or even just like carbon fiber is stronger than steel. What they're usually saying, they're not saying like one strand of spider silk or one little piece of carbon fiber is stronger than the footing or a big giant steel beam. But they're saying if you had a big giant piece of carbon fiber or a big giant piece of spider silk that was kind of the same strength for area as the small normal size one, it would be able to handle more force. And so when we think of materials in engineering, we think about the material properties will be something like, okay, how flexible is this material? How strong is it? There's also like not just the strength, but its behavior when it gets close to breaking. So things that are ductile, they stretch for a while before they break, or things that are brittle, they snap very quickly. And when you're designing something, you think about all these properties, and sometimes you combine materials. So you talked about concrete bridges and concrete roads and concrete structures are reinforced with steel, steel rebar and steel structures inside them. And they do that because concrete is incredibly strong if you're like standing on it or walking on it or driving a tank on it or something. But it's not very strong if you built a pure concrete beam and fixed it on both sides, and then you stood in the middle of it, not stood with a person, but put a huge load in the middle. It's going to bend and it's going to snap and crack because they're not very good in like in bending or in kind of stretching. They're good in compression. So you put steel structures in there to make up for that weakness. You combine them and you make a combined or a composite material.
Okay.
And you're taking advantage of the good properties of the concrete, and not just properties, but also economy and building capability, manufacturability, and then the good properties of steel and mixing them together. And engineers do that kind of stuff all the time. We play with materials. Materials is a really important part of making any product, is how it behaves. So it's mechanics, how you're going to make it, and what materials you're going to make it out of. We say mechanics, materials, and manufacturing. Actually, like the 3 M's. It's kind of like you have to think about all 3 of those things when you're designing a product or solving a problem with a physical system.
Okay, awesome. And I did have a materials question a little bit later, but Matt or Cameron, did you have a question here?
Well, I was just thinking it probably goes into a lot like when you were talking about putting something up into space or something, a pressurized thing. You got to look at the how the material reacts in the environment as well, especially with the extremes of hot and cold that it has to go through. So what I was watching, I don't know, some silly physics experiment on
all physics experiments are silly. Continue.
Okay. It was on Jimmy Fallon. Anyway, it was they basically superheated this drum with water, like heated it up so it was all gas in there, and then they put it in a bucket of ice, and the steel drum just collapsed. Right? Yeah. So I mean, it was basically showing that the tolerance is like the atmospheric pressure. I'm sure you have to take things into that when you're designing whatever you're doing, like where it's going to be, so you don't have something like that happen.
Yeah, that's right. And so, I think I've probably mentioned the word load or force a lot of times, several times already. So we often say, I talked about when you're trying to solve a problem, you kind of have to gather what all the requirements are for this potential solution to the problem. And usually we say, let's define the loads. Let's decide what the loads are going to be. If it's a bridge, it's like how many cars could fit on this bridge at one time when the wind is blowing and maybe when an earthquake is going, right? So how much load could it handle? But more broadly, we actually don't just talk about like forces like single forces or groups of forces. We talk about environment. What's the environment? And people hear the word environment today, they think of like, well, it's Earth Day. The environment has to do with like the Earth and our planet and pollution. Well, we talk about environments, and it could be the thermal environments. It could be a vibrational environment or a dynamic environment, like a rocket launching in space undergoes tons of vibration, and you have to design that spacecraft so it's either isolated from that vibration by some structures, how it attaches to the rocket, or it can handle the vibration. And then there's other environments like, is the structure going to be near salt water? And there are handbook standards for like how you test things and how you qualify things for real world use. And you might have to like meet like a salt spray requirement. Not that the salt spray will damage it today, but over many years of salt spray exposure, that environment could cause certain materials to break down and corrode and rust and break prematurely. So environment can be like all the materials it's exposed to, all the temperature swings it's exposed to, solar, UV, radiation. If you're going out in space, you have to have rad hard electronics. So there's all these things that we just call kind of generally loads and environments.
Okay. Yeah, and I'm going to have a few more questions once again about potential explosions and catastrophic outcomes of engineering projects. But before we do that, I do have a question about, I ran across, and I'm going to butcher how to say this, and we do have worldwide listeners, so I do feel bad, but D'Alembert, the D'Alembert principle, and I was entirely unclear on what that was.
Yeah, so I think it's pronounced D'Alembert.
I was close.
D'Alembert's principle. And you asked me about this, and I was like, oh, I kind of remember what that was. Let me look it up. But I don't want to deflect the question, even though I wouldn't have known it if you hadn't prepped me. But it's a good example of something that's not so much like a physical principle, right? Like you think of like Newton's laws of motion, like, everything, there's an equal and opposite reaction, and an object at rest will stay at rest unless an external force is applied to it. Those are like kind of physical principles and kind of how the world works. There's also all these things that are kind of more like mathematical problem solving approaches. And D'Alembert's principle is one of those. And we talked about dynamic and static systems. And D'Alembert's principle is simply one way. So solving a static problem is quite simple, because you basically say the sum of all the forces equals 0, because nothing's moving. There's no acceleration. And once you learn how to solve those, then it's like, okay, now it's time to learn, and this is like in the progression of getting your degree in engineering. Now we're going to learn how to solve a dynamic system. And kind of one of the first ways you learn how to address it is D'Alembert's principle, where you say, we're going to treat all the forces as real forces, and we're going to treat the acceleration that the system would actually go as inertial forces. And you could still say the sum of all the forces, meaning the real forces and the inertial forces, equals 0, because you kind of handle the accelerations as if they're like an inertial force. An inertial force, that's a complicated word, maybe not a great word for a layman, but it's simply like just a problem solving approach for a certain class of problems. And there's tons of those. And you learn them in all your classes. And then once you go into the real world, you kind of only focus on the ones that are, applicable to your industry or your field. And
Sure.
also, we move far beyond hand calculations and a lot of stuff we do where we build models on a computer, and the models are big complicated systems, and the computer programs are solving those equations, but in large arrays simultaneously, and doing what looks like what ends up being a simulation of how something moves, how it behaves when you apply certain loads or environments to it. And it does all the calculations for you because there's far too many calculations for a person to do by themselves. And all the simple calculations you might do at the start to figure out if you're in the ballpark, and then you use these other computers, software to solve the problem in much greater fidelity. And so, yeah, that's my kind of tangent to address your question about D'Alembert's principle.
No, that's great. Thank you. Okay, let's talk about a couple scenarios that I'm personally familiar with that I've always wondered from either mechanical engineering perspective or just from a engineering perspective, I guess broader. Let's talk about roller coasters, for example. There may have been an instance where many or all of the co-hosts on this podcast, besides yourself, Curtis, rode in a roller coaster for much longer than seemed appropriate. And I'm pretty sure that the employee running the roller coaster had either quit or fallen asleep or died. And besides the physical discomfort I was experiencing, there was also this question of how long can this thing operate continuously before we die? So when you're like you have a specific project you're dealing with, be it a roller coaster or a space, can you establish this thing can only run for this long? This is the real world speed limit for this. This is and how do you, I guess, set these they're not tolerances, but the I guess limitations or whatever.
Yeah. So in every industry, they establish or they're whether it's formal or kind of more best practices. There's established margins of safety or safety factors or factors of safety. There's different ways to say them, and they all kind of mean the same thing. So, for example, an aircraft that has people on it, they'll design that aircraft with a certain factor of safety. So after they've done all their calculations, they've designed and you've used calculations to come to a design for how big the structures that attach the wings to the body of the airplane, or how big the structures that attach the landing gear to the aircraft or whatever, how big those need to be. They then say, let's make them a little bit bigger based on some factor. And so a passenger airplane will have a certain factor of safety that's pretty high. And I don't even want to say some numbers just in case I'm wrong and that freaks somebody out or whatever. I don't want, but let's say in a particular system, I say, I'm going to assume that after I've done all my calculations, if I make this structure 50% larger, I've got plenty of conservatism that it won't break under the loads that I assumed happen. And loads that might happen beyond what I assumed happen are such a low percentage of chance that I'm in the clear, if you will. And I would write my report and say, this is the safety factor that we assumed when we decided how big this metal axle needs to be. That's an example of this buffer that we build in. Now, if I am producing a design purely based off a computer simulation and I've never built it and I've never tested it, I might use one factor of safety. And then once I've tested it, I now can establish my factor of safety, what it is. And I might say, okay, the next one we design, or now that we've tested a prototype, the one we actually design and build, we're actually going to get a little bit closer to that, cut that margin down a little bit because now it's tested in the real world. And, there's all these unknowns,
right.
Is the load really what I think it is? Is the friction really what I think it is? is the material that I bought from some supplier going to really perform the way that the supplier sold me on it? So I'm assuming all these errors or potential sources of error or failure, and I'm kind of combining those together and using those to decide when I'm doing my calculations on paper. I'm going to use one safety factor. Once I've tested, I'm going to use another safety factor. Once something's been in the marketplace for years and years and years, then I might basically say that, oh, that's basically established by practice that we're not anywhere near failure. So now you talked about like how long can something run? Something like a roller coaster and something like I don't know, like an animatronic figure next to a ride. Maybe there's like a dinosaur that lunges at the passengers every time they go by, right? Those things, it's not just about how strong, what kind of loads they can handle like one time, because metals degrade and a lot of materials degrade over time. And so you have to establish like a lower strength for a certain number of cycles. And sometimes that's some materials, every cycle you add degrades the material forevermore. So it will not last forever, no matter what you do. There's other materials where as long as you're below a certain threshold, you'll never reach that life limit. And we call it fatigue when something fails after many, many cycles, versus like a strength problem when something fails one time because you put too much force on it the one time. So fatigue, I always kind of joke that themed entertainment projects or roller coasters are fatigue testing machines, because they do the same thing over and over again with more or less the same loads. I mean, you might have heavier riders and lighter riders, but for the most part, they do the same thing over and over again, repeated fashion for years and years. And so they might say, we want you to design this so it will last 40 years or 20 years. And they tell you what like the duty cycle is, which means how many times it will run a day. So you might assume 16-hour days, 365 days a year for 20 years. And if it goes around the track and it hits this one particular curve really hard, and that's like the limiting curve, that structure, then maybe you only have one event every time it goes around the vehicle, the curve. But maybe it hits a curve and the whole thing vibrates like 100 times after it hits that curve. Now you've actually got whatever your number for 20 years of rides times like hundreds. So you have to factor that in. And you don't want that. You want to avoid any of those kinds of dynamic behavior, because you might not actually be able to decide or calculate or even measure how many actual times it vibrates. So it's much better if you don't have those kinds of dynamics in there. You do a calculation, and yeah, they put some padding on there so that it will never happen. And they designed for like the 95th percentile weight person, filling every single seat in the vehicle. And they might test, I know for certain that they test by putting these dummies that look like a person without legs that you could fill with water. They're like these big water tanks that look like a person's torso, so you can strap them in and put a seatbelt on them. And they'll fill the vehicle with these dummies, and they'll fill them up with water. And they have a water line they fill them up that represents like a 50 percentile person and a 75 percentile person and a 95 percentile person. And they'll instrument the vehicles and they'll run them with these different scenarios, and they'll take data, and then they put that data back into whatever calculations or computer models they use to size everything in the first place, and make sure that the simulations they ran are good enough for what they actually collected from their tests. So you can rest pretty easy that in the themed entertainment industry, they're very risk averse, and they're very worried about something looking bad or happening, and they designed for that.
Okay.
I think you were kind of asking, is there like a big book of what a body can tolerate? I think is what Carl's wondering. Like if I put Steve in this gyroscope, like how long before Steve loses conscious, or
Poor Steve.
Yeah, fortunately, there are a lot of people. Most most of these were like government funded projects back in like the space race era and stuff. Military funding helps us figure these things out, and then they document a lot of it because it's paid for by taxpayer money. But yes, there are factors of like, if someone goes at a certain G load or certain multiples of gravity facing forward, how many times multiples of gravity before they would pass out, or if they're facing backwards, or if they're going sideways. And so in the entertainment industry, they want you to get a thrill, but they don't want you to get sick. I think they call that like a code V, when someone vomits on a ride, and they don't want that. And they want you to feel like you're getting the best thrill of your life, but that you don't come off and go like, I'm never riding that again because I felt really sick. And they also don't want you to get hurt or pass out or any of that. So they have pretty low accelerations, and you can take your phone and you can download an app that's got a little accelerometer that tells you. And people do that on amusement parks all the time. Like, they're like, what was my vertical acceleration? What was my forward facing acceleration on that ride? And they're only like, like 1.2 multiples of gravity going forward or going up or down, so it's a significantly higher that you could handle before you passed out than what you're experiencing on even like the worst like gravity drop rides and stuff like that. Now, you also asked about like speed limits for components. If I'm a manufacturer making like wheels or bearings or anything like that, I will test the limits of my component, and I will publicize it, and I'll add my own factors of safety in there, and I won't tell you what my factors of safety are. So I will just say like, this wheel is designed for a certain load, how much weight it could hold, and what speeds it could spin at that weight. And it might even have like a chart that says, if you exceed the weight, the speed limit goes down to a point where it's like derated to like, don't exceed this speed and don't exceed this load. And I publish that, and then my hope is that if you come back to me and say, hey, your wheel failed on me, I can prove to you, well, I have test data that says that the only way it would fail is you ran it too fast, you put too much load on it, or you ran it for longer than you should have without re-greasing it or doing inspections or whatever. So I want to protect myself and sell products that people are happy with and perform the way they expect. And so I will rate my product through testing and other programs in order to be able to provide that data. And then someone integrating that into their system has to make sure they're following the way something should be attached, the way it should be used, if it's being used in like the wrong temperatures or in the wrong environments, like the salt spray I was talking about. Maybe it's a stainless steel bearing, but maybe it's not sealed or something like that. I want to protect my product and my business and my customers and their clients or whatever by producing data sheets that tell them the speed limit and the load limits and the life limits of everything I sell. And if I'm a consumer of those products and integrating them, I will probably do my own testing as well to some degree to see if I can confirm that I'm happy with the way that product is performing in my system.
Right. A few of the way you just described engineering a roller coaster reminds me of Tim's job as a middle school teacher. And I don't think there are a lot of models that predict how long a sane person can tolerate a certain load of middle schoolers.
Yeah,
But Tim has exceeded it.
The teaching industry is also a fatigue experiment of a different sort. And, we find that as we leave that we are definitely not rated as high as we were when we started.
Yep. Yeah, we got fatigue, we got pressure, we got stress. All these words in engineering means similar but still different things from what they might mean in other industries, and
Right.
but they're also to some degree analogous, right?
Right. Exactly.
And I think Curtis said in the previous statement, basically, Carl, you're just weak sauce on the ride
That's
that
true.
you went on.
Exactly.
So
I could have tolerated it for probably another couple days.
yes.
So, okay, a few more questions here, Curtis. Thank you. It's been great so far. And okay, the SpaceX recently launched a rocket that exploded.
Yeah.
I'm guessing that they've ran a significant number of computer simulations and probably tested components beforehand, right? So how
That's right.
often, like, I guess the question really is, you've kind of described like an iterative process as far as like computer simulation and testing, but we still see explosions, we still see massive collapses of things that should have probably been engineered to tolerate that. What how often do we see these catastrophic issues, and is that always because of an engineering failure, or are these outside forces that were completely unforeseeable? So I mean, I guess obviously you need to test real world test, but shouldn't computer simulations be able to handle a lot of this?
Yeah. So the stuff that's like kind of the high profile and makes it in the news, especially with like the private space, new space, right? All that stuff is pushing the limits of of what we have done, right? Or going past the limits of what we have done. And so, and they make the news, right? But think of like all the products that you use every single day. I mean, whether it's like a skateboard or your phone, there's a lot of products that they're making tens of thousands of them or millions, and they're only breaking when we completely abuse them, or on a very small percentage. And so that stuff's kind of already been done, and you might innovate like little by little, but the testing will go along with that. So some things though are just so far beyond what we've ever done that when you do a simulation of something, often you're making assumptions about what the loads in the environments are, and you're making assumptions about certain things that might not be like material strength, but it might be like the behavior of like two parts that are in contact, something that's less that's that's not as easy to understand just by like saying, well, this material behaves this way and this material behaves this way, so when we put them together it's totally clear how they behave. That's not always true. So in your simulation, you have to define all these things. You have to define like the material properties. You have to, I mean, you're telling the computer what parameters to put in to the equations that computer is solving. And if you put garbage in, you get garbage out. And if you make bad assumptions, your solution won't mean anything. So when we're developing new products and doing new things, we might initially start using a simulation to understand the problem, but that doesn't mean that we have 100% like solved the problem. And so one thing simulation does though is it can significantly reduce the cost and the time to get to a final product, because instead of building 100 iterations and testing each one and then figuring out what failed and making a change, you can get pretty close by doing 100 different versions in simulation. And then you build less prototypes in between, and prototypes take time and they cost money. And also, the further down a path you get of a design, the more expensive a change is. So if I've never built something and I want to make a change on my computer model, that costs almost nothing. I run the test, the simulation, I assess the results, I make some little change in the software, and I assess the results. I can do that all day for way cheaper than I can. Let's make a drawing, let's cut metal, let's assemble everything, let's do our test. It failed, let's do some kind of forensics on it, and then make a modification and then rebuild it. The further you get into the design, the more expensive every change is. So you use simulation to save time, save money, and try and capture like a much broader combination of loads. And once you've kind of figured out like what are the worst cases, then you test the worst cases, because your simulation has predicted that everything else is fine as long as you can show this particular load is okay. So you test way less. But in something like flight, if you're sending people or super expensive things and you only really get to do it once because it costs so much to do it, or there's lives on the line, you also test. You don't just sit there and rely on your experimental results or your analytical results. And so I don't know. I often read headlines, but don't read too far into the news. But with the SpaceX thing, it was like the first time they'd ever launched that rocket combination with that spaceship. It's a huge spaceship. I mean, I can't remember how tall it is. I think it's like a 30-story building or 40-story building. It's size. Yeah. And so they were, I don't know, maybe Elon Musk said something like, well, just the fact it got off the ground was a success. And, they'll always spin something, right? But it
Right.
really, everyone was expecting that the first time you launch something that big, that different than anything else that's been launched, that a failure of some kind, whether it's loss of communication or complete explosion right on the pad or something, is expected. So they instrument the heck out of the thing and collect the data, expecting that even if they lose everything, they'll have the data to help them with the next step. And
that makes sense.
in a lot of companies, I think SpaceX is one of them that's kind of led with this, is you test like you fly. So you test with the exact components that you're ultimately going to fly with when you send a real precious payload up. And that's changed, that's guided their design philosophy. They don't use exploding bolts or things like that, because once you explode the bolts, you can't reuse those components for the actual flight. So they test like they fly, and if something fails during a test, you have to expect it's going to fail during the real production flight. So you don't test with substitutes, and
Right.
simulation is a substitute. So ultimately, you have to do some tests even after all the simulations are done.
Right. Cool. Okay. 2 more questions for you. You've talked about materials a fair amount. We've talked about materials at the beginning of the podcast. And engineers are familiar with obviously lots of different materials and the benefits and of different materials under different loads or whatever. But I'd imagine, and I guess this is the question, how often are materials dictated to you as an engineer versus being able to say, oh, it would be best if we had adamantium in the case of X-Men? Just to be clear, I don't actually believe that. How often do materials dictated to you?
Yeah. I mean, not super often, but it's more than just the performance of the material, right? There's so many factors. Like cost is a huge factor when you're making things and making real parts, right? I mean, if I want to just design something on paper and say I invented this really cool thing, I can make it out of whatever material, no matter how expensive. But if I'm actually going to produce it, there's a market force at work. So steel is significantly cheaper than aluminum, and steel is cheaper than stainless steel. But I might be operating in an environment where steel is going to rust. So the requirements, the environments of the system, where it's going to be used, how much it's going to cost, those kinds of things end up like shrinking your design space or your choices that you can use. Whereas if something is so important that we do it, money is no object. And in aerospace, I wouldn't say money is no object, but every weight drives everything. And so they're using the craziest materials, the strongest grades of aluminum, which costs a lot more than like the normal aluminum that you and I like use in our everyday products that are made of aluminum or whatever. But the strongest grades of aluminum, because you can make the materials thinner and lighter and get the same strength. Or they're using very expensive materials like carbon fiber and other composites that are like non-metallic, because those are so much lighter for a certain strength. Plus, you can tune them in the shapes you want to make them so that they can handle strength or loads in a certain direction, the way they're going to be used, or maybe you're designing for stiffness. So all these things get kind of requirements usually shrink down the materials that you could realistically build with. And those requirements are more than just performance requirements. There are also market requirements like cost, and environmental requirements like material interactions. And also with space, if you have optics, which a lot of space does because there's telescopes and things up there, you don't want to cloud up your glass optics. And so you can't send any materials up there that might, as they go into space, what they call outgassing. And as it kind of goes into the vacuum of space, produces like vapors come out of it. Certain plastics and adhesives and things like that will outgas. So you have to choose a very specific adhesive or a very specific material that won't outgas, not because cost or strength, but because your most important reason of sending that thing into space, like the telescope or the optics, can't handle being in close proximity to certain materials that might be super cheap, readily available, and strong enough. So once in a while, you might have a situation where the marketing team, is like, we want to develop this product, and it's got to be made out of carbon fiber because, ooh, shiny or something.
Right.
And then, engineers are like, okay, we understand those requirements and we'll see what we can do. But often in the industries I work in, a lot more it's the environment and the performance and then the cost, rather than just somebody saying like, we want to put on our shiny commercial brochure or our cool commercial that this is made out of carbon fiber or something like that.
Yeah, right. Okay, well that's good to know. So we're not compromising engineering quality in the name of marketing very frequently, is what you're saying.
Yeah.
At least not in the big projects, the big name projects, the high risk projects.
Yeah. Now, I mean, another example though is like, it's not just about like, ooh, that's shiny, we want to advertise we have that, but what if something's like not an environmentally sustainable material?
Right.
It might be okay to put that on like a spacecraft or a satellite, but it might not be okay to put that on a product that like people are using in their cars with they're driving their kids around, or whether it's like safe, a hazardous thing or makes you sick or something, but it could also be like just the fact that it's socially responsible, to make things out of like recyclable materials. That might be a requirement by itself. Say, okay, I'm going to eliminate all the materials from my choices that aren't recyclable, and now I've got a certain limited number of materials that I can use. So those are real, but again, it's those requirements. Engineers will use those and they'll figure out how to work around them, rather than like compromise because of that.
Sure. Okay. Last question. We're going to skip one of the questions that I think we're going to open us into a different field of engineering. So for the sake of time, I won't ask you what fluid mechanics is, but what you've been in the field for more than 15 years now, right?
Yeah.
And so it's not like it's been since the Stone Age, but I'm guessing in the last 15 years, you've seen a fair amount of change in obviously software quality, in the ability of computer models to be able to aid in engineering. How has this new technology affected your work, and what do you see coming down the pipe?
Yeah. So, I mean, technology can influence engineering in a few different ways, probably more than just the few that I'm thinking of. But, when I was in school, it was already at the point where we had computer graphics, where we could do basically all of our computer drawing and design using CAD software, computer aided design software, which is like, 3D modeling, build a part, then you build another part, and you can put them together and manipulate them on the screen. And then you can produce drawings all with the computer. It was before my time that people were actually standing at like drafting tables, like drawing the parts and dimensioning them. But a few people I work with, like they worked in that time. So that's an example of like an advance in technology that made it so that our engineering job is significantly different. I don't have to carry around like a case full of like pens and protractors and stuff in order to do my drawings. I sit at a computer, I have the software, and I can create these 3D models, rotate them, look at them from every angle, figure out how things go together. So that's a tool that has made the process of engineering that much better. And it's not just like, oh, now life is so much better and simple, easier, and I don't have to work as long. Instead, it's now let's make more sophisticated products and let's push the limits further because we can. Because we have the tools that allow us to now solve problems or solve harder problems than have already been solved. So that's one way. Now, there's also like technologies that influence how the products, right? So you think of like a battery technology has significantly changed. And that's why we can carry a cell phone around, right? And that's why electric cars are feasible and profitable today. That's why, you know, there's like little drones. Not only are they affordable, but the fact that you can have something fly for several minutes or several hours is because battery technology has changed. And so every time like a new technology like that or a significant shift in technology happens, people go back and rethink all the products we have and say, now that we have this, I can make a new innovation of you know, applying this new technology to like an old problem. And it, you know, it might be something like a battery powered hair dryer, right? Hair dryers have always existed. You plug them into the wall, they generate a huge amount of heat. They actually use quite a lot of energy. But so now that we have like lightweight batteries and you can recharge them easily, someone might think, I'm going to innovate by just marrying these two things together, a battery and a hair dryer. And you know, the first time you do that, there might be some engineering involved, but once it kind of is like done, after that, it's just like product development. It's not really engineering, but anything like that, where a new technology, a significant shift in technology happens, there's an opportunity to like revisit every single product we have and modify it to accommodate that new technology and make it like more convenient or make life better, make the world a better place. But there's also maybe problems that have kind of been sitting on the shelf that people have been thinking about for a long time, and now they can do them because we have these new technologies. And then usually as you're kind of working with these new technologies, new problems arise, and now you have to solve those problems. And so engineers go to work on that. And like gene sequencing is another one I was thinking about when I was thinking about this question a while ago. The fact that we can like sequence genes, you know, you do that in the lab, you do that with like, you know, I don't know how they developed that technology. I've never been in like a biochemistry lab to do that, but they're doing that by hand, very slow, very meticulous with microscopes and all these things. Once they figured out how the process happens, they say, to do this at scale, we have to develop machines that package the process and automate it. And those machines might need like a lot of power. They might need to move little tiny things really, really fast. They might need to handle fluids in a way that we've never had to handle fluids. And, you know, there might be a lot of vibration. And if you have too much vibration, it might damage your sample. So now engineers come to the table. The scientists say, we figured out this problem. Let's figure out how to productize it or package it. And the engineers get invited to the table to work on solving all those things so that this new technology can actually, a technology we never even knew about, totally new thing, can now actually be done. And then once it's figured out, so now can we make it small enough that every hospital could have one of these things? Or now that we've solved this problem, we understand something we never understood before. You know, whatever that happens to be, let's take that to market. And again, the engineers take what the scientists have figured out and figure out how to like make it a physical reality.
Wow, that's great. This has been wonderful. Thank you, Curtis. I appreciate all the insights and the understanding of engineering, that mechanical engineering or all varieties of engineering that's been great. I think great for the audience. One thing for Tim before we sign off here, Tim, per a source, and it may have been me, but someone reliable said that you had recently become one with a chat bot, like one of these new AI. So I think it's fitting to give Tim the final word on engineering. Tim, what did the AI teach you?
You know, the future is sorry, I got to give a second for the AI to process that question. And no, well, you know, it's a lot like the Matrix, and so yeah, look forward to you. Everyone will walk around hooked up to the grid, and it's going to be wonderful.
Okay, good. Well, at least we know that you can survive in as much as Tim isn't a good example of surviving. Okay, thank you, Curtis. On a real note, I really appreciate you coming on and doing a podcast. It's great insight into the mechanical engineering world and all the different expertise you have. So thank you.
Good, thanks. It was really enjoyable.
Well, thank you, and we'll sign off, and we'll see our listeners back. Here, they will hear us again soon. So we'll see you next podcast.